Hello and welcome to the first episode in my series going through the history of neural networks and machine learning, stopping at different ML papers that were pivotal to the field and then re-implementing them in Python. For the first episode, we are going to be talking about multi-layered perceptrons and backpropagation, which is arguably the bedrock for basically all deep learning and neural network type activities. So, the first thing I'm going to do in all of these episodes is read the papers. Right? So we're going to read the original paper, and then we're going to implement it in Python. So, let us begin by reading the paper. Here is the original backpropagation paper from authors David E. Rumelhart, Jeffrey Hinton, and Ronald J. Williams. You will hear about Jeffrey Hinton again later, and again, because he is a pretty big name in neural networks and deep learning. So he will keep showing up. So first, as always, whenever I do read a paper, we'll start with the abstract. We describe a new learning procedure, backpropagation, for networks of neuron-like units. The procedure repeatedly adjusts the weights of the connections in the network so as to minimize a measure of the difference between the actual output vector of the net and a desired output vector. As a result of the weight adjustments, internal hidden layers, which are not part of the input or output, come to represent important features of the task domain, and irregularities in the task are captured by the interactions between these units. The ability to create a useful new features distinguishes backpropagation from earlier simpler methods such as perceptron convergence procedure. So, in essence, what they're saying here is that they've come up with a new way to effectively change the weights of a neural network, right? Because previously you had perceptrons, for example, like the perceptron machine, that you kind of had to like manually adjust the weights, and if you were doing it automatically, it was like not very good. Here they're introducing backpropagation, and backpropagation is a much better way to actually adjust these weights. Now, let's actually discuss what is backpropagation, and to do that, and to actually find out what it is and how it works, we'll need to read further into the paper. So, there have been many attempts to design self-organizing neural networks, right? For example, the perceptron from before and whatnot, right? And so the aim is to find a powerful synaptic modification rule to allow an arbitrarily connected neural network to develop an internal structure that is appropriate for a particular task domain. Note, arbitrarily connected. This isn't specific to a specific type of connection. This is, you can connect them whatever way you want, and then it will just work, right? So, the task is specified by giving the desired state vector of the output units for each state vector of the input units. So, if we go to the diagramming, if we have the expected output state vector, right, so this is a vector, that's the expected output, and then if we go back here, it's a state vector of input and output, right, so that's your task, and so this is the input, right, so you specify a task by giving it an input and an expected output. Then you have some magic box in the middle that goes from input to expected output, right? So this is what your neural network would be. It's an arbitrary function, right? You take a function of n inputs, which is your input, and a function of n outputs, which is your output, right? Let us continue. And so, if the input units are directly connected to the output units, it's relatively easy to find learning rules, right? Because it's just like, it's a linear function. This is just linear regression, you're doing linear regression. But if they're, wait, hold on, yeah. And it will adjust the connection so to progressively reduce the difference between the actual and desired output vectors. Again, linear regression. Learning becomes more interesting, but more difficult when we introduce hidden units whose actual or desired states are not specified by the task, right? So, in essence, what we're saying is the old technique that was very easy, linear regression, all it was you effectively had input, output, you kind of effectively just do one matrix multiply, right? So, your entire function was just multiplying, like your entire neural network was just multiplying by a matrix to go from input to output, right? Like, this is just a one-layer linear approximation, and this would go from the input to the output, right? And you could like optimize this with linear regression and whatnot, but it's a very simple thing to do. What we're effectively doing now is having hidden layers, right? So, in essence, you have your input. I'm going to bring over the weight matrix. This then gets converted into a hidden state, right? So this is your hidden state. Then you again apply the weight matrix, and then you get your expected output, right? So in essence, what you have is you have a hidden state. Now, this is much more difficult, right? Because like, which one of these weight matrices do you change, right? Like, how exactly do you optimize these numbers so it's better, right? And that's what backpropagation is. Backpropagation is a way to decide how to optimize these numbers and calculate how you should tune them. But we'll get to that further along in the paper. First, we have to talk about what does it mean to go from a layer to a layer. So, the simplest form of the learning procedure is for layered networks to have a layer of the input layers at the bottom, any number of intermediate layers, and a layer of output layers at the top, right? So, they're not really thinking left to right, they're thinking bottom to top, right? And bottom to top, we'll see that come up later and again, right? Because attention is all you need. The original Transformers paper also had inputs at the bottom, outputs at the top, and the way to traverse up. For me, personally, I prefer a left to right, so I will just go ahead and continue having everything go from left to right. And so, now they're talking about what exactly is a neuron in this case. So, you've seen the fancy diagram of a neural network that you have some neurons, and then there's like another set of neurons in the next layer, and then there's your output, right? So you have your input, your hidden, and your output, right? And like all of these neurons are like connected to all of the other ones, right? Right, so all of these inputs are connected to all of these outputs. This is getting a little bit messy, but like it can be fixed. Right, like all of your inputs connect to your hidden layer, and then all of these connect to here. But now we have to figure out, like, what exactly does this mean, right? Like, what exactly does having all of these interconnected layers, like neurons, mean? So, in essence, they specify that a neuron is, so you have the total input to the unit, so the total input of unit J, so let's say this is neuron J, right? The total input to it is, they're just saying it's the sum of the outputs of the previous layer. Like, Y is the output, X is the input, right? Like, normal functions type stuff. They're just saying it's the sum of, like, this is like I1, I2, I3. It's just the sum of all of that multiplied by whatever weight is assigned to it, right? So it's just a, like, Y equals MX plus B, right? Like, you're basically just having, like, Y equals, I guess this is the input X equals M1 Y1 plus M2 Y2 plus M3 Y3 plus B. But they have not brought in the biases yet, right? So we're going to include biases in our rebuild, but they are not including biases here. And so, yeah, they say units can be given biases. They're not really bringing stuff in, but yeah, they're just having, like, the default one does not include biases. We're going to be including biases. And then to find the output of this, like, you have the sum of the inputs. To find the output, you effectively apply this function, right? 1 over 1 plus e to the minus x. This is the sigmoid function. I do not believe they actually name it here, but this is the sigmoid function. Its derivative is very easily computed, and yeah, and so they say it's not necessarily to exactly use the functions given here, right? Like, you can change the function slightly and it'll still work. It's just they use it, and so we're going to use it, right? They say any input-output function has a bounded derivative will do, so effectively just have a function that you can find the derivative of at any given point, and the functions there just include nonlinearity, so that you can take any arbitrary function, and this entire model can't be collapsed into a linear function. Because if it could be collapsed into a linear function, what's the point of a neural network anyways? Just have a linear function, right? Now they have their total error, right? So now, okay, you've defined what a neuron is. Now what you have to do is define how exactly do you find the error, right? Because you're trying to optimize for lowest error. And obviously, if you start with random weights, you're not gonna have any like useful model because it's random, right? So you first have to find the total error, and so what total error is if you so for the final output, right? So we find total error by comparing expected output with the I should probably change this. This isn't the expected output. This is the actual output, and then other than that we have the expected output, right? So that's the expected output, right? And so their function here is basically saying C is an index over the cases. So you have a large data set, like let's assume you have like a 13,000 things from MNIST. I think that's a little bit too far in the future for this paper. This paper is from 1986. But let's say you have like a function and you have a few input-output pairs, right? And so C is like, oh, you iterate over all your input-output pairs. And so the total error of the function is the sum of all the errors of any individual case. J is an index over the output units. So if your function outputs like 10 different things, right? For example, I'll use the MNIST classification case. You normally have a neural network output 10 different numbers, which is the probability that it is any one of the given digits. And so you're iterating over those to find your total error, and it's this mean squared error, right? So you take the square of the difference between the current number, like the actual output of the model, versus the expected one, and you square that. And so this way, smaller, like minor errors, it's like less expensive, but then very major errors become much more expensive. So the model becomes a better approximation than if you just had like a linear error. And they divide it by 2. I don't know why, but it doesn't actually particularly matter for neural networks. So yeah. And so to minimize E by gradient descent, it is necessary to compute the partial derivative of E with respect to each weight in a network. So in essence, all this thing there is we're trying to figure out how, if you change any given weight by a small amount, how much does that affect the error, right? And so in essence, what we're trying to do is we're effectively trying to tune the weights until the amount of error reaches as low as possible, right? So we're effectively trying to see which direction do we tune each one of the weights so that we can reach minimum error. And so, yeah, and so then they do a little more definition, right? So this del E over del Y of S, which is basically how much, like if you change how much does the error change if you change the output of the, like any given, like neuron, right? If you change any given neuron's like weights or biases, how much does the output change? That's just the output minus the error, right? So this is the final layer. So you start by calculating the, so for the final output layer, you have another sigmoid neuron type stuff, and so you're effectively running this to find out, hey, how much do we have to change the input, right? So this will give you a calculation on like how much you have to change the input, right? And then from there, you do that one layer back, right? So you know how much you have to change the like final layer, but now you have to figure out how much you have to change the layer before that. And so what they basically say is just do the process again, right? Like find the amount you have to change the layer before, and then you get it, right? So you can see delta W, which is the amount you have to change your weight, is negative epsilon, which is the learning rate, times the gradient of error over like del W. It's a partial derivative of the error with respect to W. So what that basically means is we're going to change the weight by the slope of the error curve with respect to weight. So in essence, this is like if we tune this weight, how much will the error curve actually change, right? Like how much are they interlinked? So if, for example, lowering the weight by 1 will lower the error by 1, we want to do that. But we also want to limit it, so we're multiplying it by this epsilon, and this epsilon is just learning rate. Like how fast do we want to learn? And then what they say this method does not converge as rapidly as methods which make use of the second derivative. And so what they have here is they've added a momentum, right? So alpha is exponential decay factor. I'm going to call it momentum, right? And so in essence what it is if you store the previous, like the amount the weights changed previously, you just like keep including that into your gradient descent, what you end up with is it just trains faster. Because you kind of like imagine like you're on like the top of a hill. You know it goes down in like one direction, right? So you might as well just keep going in that direction because you know it's going to be going down there. And so this will converge much faster, right? Which is what they're saying. And now, how exactly you initialize the model? First, so to break symmetry, because at the start you have 0 and that leads to 0 and that's actually not that good, they start with small random weights. And so variants have been discovered independently by David Parker and Jan LeCun. Jan LeCun will also show up later. He comes up with a lot of important stuff later, and so he will show up later as a very important figure. And so a simple task that cannot be done by just connecting the inputs to the outputs is detection of symmetry. Right? So they just talk about a bunch of interesting tasks that these models can do that they couldn't do before. Right? So where is this, right? So you have a symmetry detection thing, right? Like, is this thing symmetric? And so you give it 6 inputs, and you have an output that's like telling you how symmetric is the thing, like how, like what is the mirror symmetry. And so the hidden layers, they take the input, they multiply them by weights and whatnot, and then they have the output, right? And so if you have like the weights starting at 0, the model doesn't actually kind of know what direction to go in because you're dividing by 0 and a whole bunch of nasty stuff. And so now if you start by randomizing these somewhat, then the model is able to train much better. And that's what they're saying. And now, in essence, as a summary, all we're doing here is we take the difference between the expected output and the actual output, and we find out how much we have to change the weight matrix here. And then, once we know how much we have to change the weight matrix here, we go backwards another layer, and we find out how much we have to change this weight layer matrix so that we can change this hidden state most effectively. And so then, now, what we can do is we can actually go out and we can build this in Python. So, what exactly are we building today in Python? Right. So obviously, it's a simple neural network as a function approximator. We're not going to go up to MNIST just yet, but what we're going to do is we're going to have some arbitrary function, right? So probably like some tanh based function, and we like layer stuff on there and whatnot. And then we just have a one input, one output, really simple, maybe like a few hidden layers, neural net as just a function approximator. But we will be doing this without any of the built-in gradient function or like helpful tools and whatnot. So, for example, this would be like the linear layer in like PyTorch and whatnot, right? Where it's just like, we can just be like, we have a function, here's our input, here's our output, just throw in 10 linear layers, solve the problem, right? We're going to be building that ourselves, because that's how you learn, right? So we're going to be building these ourselves, and yeah, let's get building. Okay, so it's done installing. And so now, what we're going to do is we're going to actually go into the code. So first, let's go into the folder, then let's nvim main.py. And so the first thing we're going to do is we're just going to install JAX and JAX NumPy, right? So we're just going to set up the libraries, and then we're also going to set up the activation functions, right? So here we're using sigmoid, right? So if we go back to the original paper, we can see that they're using 1 over 1 plus e to the minus x, which is also exactly what we're using, 1 over 1 plus e to the minus x, right? Except we're doing it in JAX and Python, and so it's going to look a little bit different than the math notation. And we also have a derivative because we need that to calculate the backpropagation, right? Because we need to start at the end, we need to find out what we need to change each of the gradients by to actually get to the final outcome, right? And so now what we're going to do is we're going to have the code to actually go ahead and run the model, get the forward pass. So we're going to be saying output is a list, because what we want is we want to set up all of the outputs. Then we're just going to be going through the length of weights, because that's also the number of layers, right? Because remember, each layer has a weights matrix and a bias matrix, and so if we have the length of the weights matrix, we also know how many layers are in the model. And so if we're in the first layer, we'll just have the input data as an input, but if we're in any further layer, we'll have the most recent output data, because what we're going to do is we're effectively going to be stacking outputs, right? So we're going to store the outputs of each layer, and we're going to return that from our forward pass, right? So outputs is this, and then we're just going to go through, and we're just going to return the outputs, and so we what we're doing here is we're doing a dot product between the input data and all the weights. And so if you go back to the paper, you'll notice that it's actually supposed to be a sum of YMI times the weight, right? But this is more computationally efficient, and it's the exact same thing mathematically, right? So if you remember from linear algebra, a vector times a matrix can also be rewritten as a list of variables times a list of weights in like a linear function, and this is just a linear function. And then we append the sigmoid of the activations, and sigmoid is an activation function, right? Like in more modern times, you'd use like ReLU, or GALU, or SWIGLU, or any of those linear units. But here we're using sigmoid because that's what the original paper used, right? All of those newer activation functions, they're a much newer concept. Next, what we need is we need a backwards pass. So, in essence, here's the backwards pass, right? And so let's just go through this nice and slowly. We're going to take in the outputs, right? Because backwards pass is after we've run through the model, we need to start at the end and go backwards to calculate the gradients, right? And so what we have is first we need to get the number of layers because that's a nice thing to have here. And then we're going to default weights gradients and bias gradients. Weights gradients is effectively going to be a copy of all of our weights, except it's all 0 at the start at least. We're going to insert values based on after we've calculated them. And the same thing for bias gradients. Bias gradients is also going to be numpy zeros like, so it's just a bunch of zeros, but it's in the same shape as the bias matrices, right? I guess this is a bias vector because, yeah. Then we need to calculate the error at the output layer. So, in essence, if we go back to the paper, we are calculating the yjc minus d of jc. Now, of course, we're not actually squaring it because it doesn't actually matter that much because we're trying to minimize it anyways, so it doesn't matter if it's squared or not squared or whatnot. So, yeah, we're just having the outputs minus the target data. Next, we calculate the gradient. And so what the output gradient is you take the total amount of error and you multiply it by the sigmoid derivative of the output. So, like, if you change a little bit of the output, how much does the error actually change, right? So if you have like 10 different like outputs for your model, if you change one of those, how much does the error actually change? And that's what we're trying to calculate here. That's the output gradient, right? Now what we do is we go through the model in reverse, right? So for every layer in the model, we go backwards, right? So last layer to start. If I is the final layer, so num layer is minus 1, what we do is we take the weights gradient is just going to be the JNP.outer of outputs times the gradient. So what that is that just generates a matrix that, given an input and a like output, what we do is we just effectively generate a matrix that will take you from your input to your output, right? So effectively back generating a matrix based on what we want the multiplications to be, right? So we effectively say we want if the weights to change by what will let us lead to the outputs changing in this way, right? And outputs of I minus 1. Yeah. Then our bias gradients is just the output gradient, because in essence what we need is if your input, like if we go back to the diagram, if your hidden state is different from your actual output by like, I guess sorry, if your actual output is different from your expected output by X amount, you can just add, right? Like if you expect 7 and you're getting 5, just add 2. And that's exactly what we're doing here, right? We're effectively going here and we're just saying, hey, the gradient is exactly what we're missing, so just add it, right? This is obviously going to be clamped by epsilon, which is a learning rate, but we'll get to that later. And our hidden gradient is just the output gradient. So hidden gradient is the gradient going into the layer. So what I've named here is you have the actual output. The hidden gradient is the gradient of what the input to it should be, and then the output gradient is the gradient of the output, right? So just a naming convention I have, and I'm going to be using it for this code. And if you're in any of the hidden layers, first we calculate the hidden gradient, right? So this is the gradient coming into it, right? And so then from there, we also calculate the weights gradient in the exact same way as before, but instead of the output gradient, we have the hidden gradient, and then the bias gradient is just the hidden gradient, right? And the output gradient becomes the hidden gradient, right? So this is just effectively bringing it back a layer, doing the calculations again, and we just go back a layer again and again and again, right? And we return the weight gradients and the bias gradients. Now we actually have a backpropagation code, right? So this is the backpropagation function, right? And so this may look a little bit long, but we'll get to it as we go through it, right? So this, we're taking the weights, biases, the input data, and the target data, right? So in essence, because we're training on data, this is a neural network, we need data. We need to feed in the data into here. We also have epochs, which is the number of times we run through our entire data set, learning rate. And so if we actually go to the paper, we can see what these actually come into the functions, right? We can see the amount you change each weight is given by negative epsilon, which is your learning rate, times the gradient, right? So we've calculated the gradient in our backwards pass. And the amount you change at a certain amount of time is also given by alpha, which is your previous delta W. And so you have this exponential drop-off. I'm going to call it momentum in the code because that will be easier to understand for a lot of people, I'm pretty sure. And so first you have to initialize the velocity of the weights and the biases, and that's also just zeros, but it will get added to over time. The loss is an empty array because what I'm going to be doing is I'm going to be storing the loss at any epoch, at every epoch, and at the end we're going to be plotting a really nice loss curve. Then for every piece of data in the input data set. So I would like to note, I am not actually doing any batching here, right? We're not doing any fancy batching. This is just a way to, batching is just a way to improve the computational efficiency of your code, but it doesn't actually matter for us here because this is an example. We're learning from this, right? We're not trying to build the greatest model here. We're just trying to learn from this, and so I'm just not going to be doing any batching because that messes up so the math makes it a little bit more complicated. So first, we have the input data and the target data, and so that's going to be the ith element of our input and target data sets. Right, pretty simple. We just take whatever data we want. And so the outputs is we're going to be doing a forward pass, right? So we're going forward through the model. Then we have a backwards pass, which means we're going backwards through the model to actually get to the actual gradients, right? So we get the outputs, and then from the outputs we get the gradients. And then for every layer in the model, we update the weights and the biases by, so we have momentum times velocity weight. So think of this as like alpha. So if we go back to here, this is the alpha times delta W of t minus 1. This is the previous velocity times alpha. And I'm pulling the epsilon and alpha numbers from here at 0.005, and alpha is 0.5, right? So here is our alpha times the previous velocity. And then we subtract that from, we subtract the learning rate times the weight gradient from there. And so we can see here, this is a minus epsilon, which is minus learning rate times the weight gradient. And so what they have here is minus something plus something else. I just have the other something minus the first thing, right? So this is just, looks nicer in code, right? And then we just update our weights based on the velocity, right? So you can think of this almost exactly like physical velocity, right? The weights have a velocity, they're going, and the new gradients, they just kind of modify the velocity. So you can think of the new weight gradients as like the acceleration. And we do the exact same thing for biases, right? The exact same thing for biases. And then our outputs is just going to come from the forward. And so then after that, obviously, what we're going to do is we're going to get the loss. So we get the outputs as a forward pass. We do it on the input data set. And then we append it to the loss. And the loss is just a square of the errors. Right? Cool. Now, what we do is every 10 epochs, I'm just printing out, hey, we're on epoch this, here's what the error is, and then when all the training is done, we return weights, biases, and losses. Cool. Amazing. Now, we actually run the model on stuff. So first, obviously, we need a data set. Now, I don't want to actually create a data set, so I'm just going to generate one from some functions, right? Because remember, all neural networks are function approximators. All they exist to do is approximate a function. Whether the function is a random math function I generated here that was meant to be a little bit kind of insane, or the function is you take in an image and you have to detect what's on the image, or the function is natural language, right? You have a list of tokens and you have to predict what is the next token, right? All these neural networks is universal function approximators. So what I'm doing here is I have a function, and I'm going to try to approximate that function. So now you have, all this is we just generate a bunch of random numbers and we feed it through this function. This function was not really made with any thought. It's tan h plus arcsine of the absolute value of the input squared. Like, there's nothing fancy here. There's no thought going into it. I just wanted to create a little bit of a like crazy function for the model to train on. Right? There's no fancy thinking or anything. Now, from here, what we have to do is we actually have to set up the model. Right? So, all this code assumes you have a weights and a biases. So, first, we get a data set, right? I'm just going to train on 100 samples, right, for 100 epochs. Nothing too crazy. This isn't meant to be a massive model. The layer sizes are going to be 5, 5, and 1. So, what I'm saying here is effectively we're going to have 35 like weights, and then we're going to have 11 biases. So, in essence, this model is going to be a 46 parameter model. So, not 46 billion parameters like a lot of the LLMs out there, but 46 parameters. And so, in order to generate these starting parameters, because if we go back to the paper, they start with small random weights to break symmetry, and we're going to do that too. What we're going to do is we're going to take, we're just going to randomly generate them, right? And it's going to be a uniform distribution from 0 to 1, right, which is the default, going from input size, layer size for the weights, and then just the layer size for the biases, right? So, as we go back here, the model, you multiply hidden state with the weight matrix, and then you add the biases, right? And so we're just gonna do that. And the input size is layer size, because the input to the next layer is just the output to this current layer, right? And so now what we have is we have an initialized model, and now we actually need to just run the training, right? So let's go ahead and let's run the training, right? So we get the weights, the biases, and the loss by just running a backpropagation. And then what we do is we import matplotlib pipeline, and we just plot the loss, right? This exists just so we can see what the loss curve looks like. Now we have all of our model training code and everything we need. Let's go ahead and train the model. So Python 3 main.py. And obviously I'm running a little bit older NVIDIA drivers, right? So the compiler expects 12.6. I'm on 12.4. But, you know, it's probably fine. As you can tell, it's training just fine. So we started off with an error of 0.98, which is very bad. But as you can see, over time, the error is going down, right? And so then it's going to train for the 100 epochs. It looks like we're already kind of bottoming out at like epoch 40 or 50. But what we're doing here is we're training the model on these epochs. And once it hits 100 epochs, you'll see a really nice loss curve showing us exactly how it is, like how it did over the time, right? And so we should be seeing the loss curve. There's a nice loss curve. We see a really nice curve, and we can see, oh, it probably at like 40 epochs, it was probably good enough. And then there's our training code. That's all you need to train a really simple multi-layer perceptron model with backpropagation in JAX, right? So we didn't have to use any of the fancy stuff JAX has for neural networks. This entire point of this was it was meant to be a really easy way to understand what exactly is going on behind the scenes in all of this, right? Could we have used JAX.grad? Yes, we could have used JAX.grad. However, the point of this is learning, and I would argue actually building the stuff will help you learn this a lot more. Now, let's get back to the slideshow to explain where does the field kind of go from there, and some extra context as to where this is used in a lot of the modern models. Now, what are the downstream effects of backpropagation? Like, where is it used? How, like, what even in the modern world is using backpropagation to do anything? Literally every neural network, right? Every single neural network you see out there, they use backpropagation in their training. They're using it to, like, generate the model. They all have MLP involved somewhere. Like, as if you look at like a transformers model, right? The feed-forward layer, that's just MLP. That's the multi-layer perceptron you've seen before, right? And then the multi-head attention, the attention layers also need to be trained. Where does that come from? Backpropagation. You have the concept of we go forward to the model and generate all the outputs from it, and then we go backwards through the model to then get the gradients, and then we put the gradients on top of the model, and then boom, there's your new like training step, and you just keep iteratively doing that on an entire data set, and then you get your model, right? So this concept that you learned today is a part of basically all machine learning. It's a concept that is very important, and the concept of going forward and then backwards is also built into APIs such as the PyTorch API, right? Where you have the model, like when you create a new model, you can define the forward, and then PyTorch can automatically define the backward. But like, you can also have the backward defined manually, and then you control the forward pass and the backwards pass. And that's the main concept, going forward and then backwards. Cool. Now, I want to thank you guys for watching this video, and I hope you stick with me, because in the future I will continue to make more videos on these topics so you can learn more about machine learning, AI, and potentially some LLM stuff down the line. Thanks for watching. Please like and subscribe. Have a nice day.